Kapachan Lao, Sawadee Kapachan Aperat, Sawadee Kapachan Talang, Sawadee Kapachan Kwan, and Sawadee Kapachan Cherapan. Thank you so much for taking the time out of your busy schedule to um, ensure you're here today for my defense. Like Professor Parkon said, my name is Sherif Shuaib, and I'm here today to present my research to you, all titled Advancing Predictive Modeling and Explainable Machine Learning in Oil Palm Industry. This research is supervised by Associate Professor Dr. Parkon Riapan and Associate Professor Dr. Jerapon. So for this presentation, I'll use this outline. First, I'll give a brief background of this topic, the motivation that led us to do what we did. Some of the previous works we looked at that made us have the research gap we worked on, the objectives we came up with, the methodology we used, the results we obtained, and how we discussed those results, the conclusions that was made from the study. I mean, we have limitations as well, and I'll conclude my study with an acknowledgement page and the references. Now, to the background of the study. I mean, I'm aware most people probably know this plant, but if you don't know much about it, then don't worry, I'll try my best to give you more details about it. It's called an oil palm. And this oil palm is a single branch tree that requires a lot of years of hard work before you can actually get a fresh fruit bunch with a very high oil content. This is according to Unigetol in 2020. Now, Southeast Asia is considered the hub of oil palm because we have countries like Thailand, Indonesia, and Malaysia as the key players in the world market. However, Indonesia and Malaysia are the dominant forces in the global oil palm market because both of these countries collectively account for 80% of total exports. Now, there are different types of oil, but 1/3 of the global vegetable oil we use originates from oil palm tree. And you can see the different crops here. We have soy. Soy can only produce 0.4 tons per hectare. Coconut, sunflower, rapeseed is 0.7 tons per hectare, but oil palm produces 3.3 tons per hectare, which is why, again, it is very important crop. This is according to Machilo in 2013. Now, what is the motivation here? The motivation is that, yes, Thailand is a key player, and even the Thai government considers oil palm a very important crop. To the extent that in 2016, the government allocated around 730,000 hectares to oil palm cultivation. And this figure has been rising ever since. This is according to Supalanya in 2019. And by 2020, Thailand's oil palm plantation covered around 10,000 kilometers squared as an approximate. And this area only ranks behind Indonesia and Malaysia globally. In fact, Krabi has the largest plantation area in this region. Ranong, on the other hand, has the high yield. This is according to Wara Chai Rongren. Apologies, if I didn't get the name correctly, in 2023. But there's a problem. Thailand's oil palm industry faces a pressing challenge of harvesting its crop prematurely. What this means is the crops do not get to be ripe before they harvested. And once you do that, the content and the quality diminishes. That is why Malaysia and Indonesia have continued to sell a lot of oil palm globally, more than Thailand. Now, AI is a buzzword being used everywhere in the field of science, in the medical field, in sports science, and the health field. Everybody's using AI. And according to Zhu et al., this can also be applied to agriculture. Now, machine learning, which is a core component of AI, is very effective in handling complex patterns of high dimensional data. And with this, I think I think this concept can be valuable for agricultural forecasting, especially in regions like Thailand. Now, before we just delved into the research, let's take a look at some of the previous works that has been done in AI or even on oil palm. First, I'll start with one graduate school and Yod Pidgeot in 2015. What they simply did was to assess the sustainable development of oil palm production in Thailand. They used an exponential growth model, and the data set they used was production and consumption data set. Supalakanya in 2019 forecasted oil palm and crude oil palm data in Thailand using exponential time series method. Now, they have 30 sets of input data they used. That's the oil palm prices, the crude palm oil prices, and the crude palm oil production. Next is Suchada in 2021. And what they did was to predict oil palm leaf nutrient status and also provide fertilizer recommendation for smallholders using a web-based AI system. They did this by using a pure deep learning-based prediction model. And the data they focused on was laboratory leaf nutrient analysis data, oil palm leaf image data, soil analysis data, and fertilizer application records data. 2023, Warachai Rongreng classified oil palm for Ranong province using random forest-based machine learning and data fusion. They used spectral data, and they also used data derived environmentally. You can also call the data an ancillary data. Yasin in 2023 followed up with what the previous author did and analyzed farmers' adoption of oil palm and to what extent the land is being allocated in northeastern Thailand. They did that using an econometric model, and they just used the primary survey data. That was done in 2023. 2024, Navarat classified oil palm bunch ripeness directly on the tree using deep learning-based image classification that was combined with geospatial analysis and GIS visualization. Now, the type of data they used was satellite cloud imagery data, crowdsourced plantation data, GPS coordinate data, and oil palm bunch data. This was done in 2024. And the last, but not the least, Puncto One in 2025 developed a smart decision support system for monitoring and managing oil palm plantations. And their aim was just to improve the productivity and the sustainability. And the method was paired, the method they used was an IoT paired with a supervised machine learning approach using regression models. The data set was a real-time IoT sensor data, the spatial location data, and plantation management and production records in a MySQL database. So these are all the studies we found. And with these studies, we realized that there are three research gaps we could actually work on: the classification dominance, the lack of explainability, and the absence of climate variability. What does this mean? So let's start with classification dominance. Now, in Thailand, we noticed that predictive research on oil palm is very limited. In fact, very few studies have offered insight into their predictions and why their models make this sort of prediction. To really buttress our at this point, we found a study which is a systematic review on machine learning applications in oil palm agriculture. This was done by Khan et al. In 2021, and he looked at studies from 2011 to 2020, and total number of studies he found was 1,060 articles. From 1,060 articles, they found an imbalance in oil palm research. Now, 84% of the studies used classification techniques, only 16% used regression methods. And when you look at the pie chart here, Thailand is just 5.71 papers, which is really small when you compare with Malaysia and the heavyweights of let's say UK and the United States of America, for instance. So that is what I meant by classification dominance. More papers are classified, as in more papers are using the classification techniques rather than the regression techniques. Also, we didn't really find any paper that had used a black box approach. What does that had answered a black box approach? What does this mean? So even though they use classification techniques, how were this classification made? They were not really, the studies did not really explain that to us. That is where explainability comes into play. Explainability is very important because, like I said, there are a lot of AIs being used everywhere in different fields. So let's say, for instance, in the medical field, an AI is asking you to take this medicine. But how did the AI come to that decision? If you don't know, I mean, you'll probably be afraid of taking that decision. That is what explainability means. Most machine learning models are black boxes. So we found out that, okay, we can actually improve the work in this area as well. And like I said before, when you look at agricultural data in itself around the world, there are a lot of stakeholders involved. We have the farmers, we have the service providers, we have the government regulatory bodies. So it's just important we provide a framework whereby everyone good, okay, this is the decision this model is making, and this is how the decision came into play. Now, for climate variability, in all the studies I showed you, none was really working or worked on the climate variability of oil palm, right? Because even though we were able to create a model and we cannot apply the model to solve a real world problem, then model, we can't really explain what the model is doing. So for this research, I decided to work on the climate parts of oil palm, which I did not see any research being done in in Thailand for now. So with that, I came up with the research objectives. The first one was to evaluate and compare machine learning models for predicting oil palm fruit ripeness and oil volume content. The second one is to improve model explainability using formal concept analysis and lattice theory. And the third one is to develop a lattice augmented ensemble model that will that will integrate the agroclimatic variables, for instance, rainfall, for yield prediction. Now, I'll move to the methodology part, and in this part, I'll first of all give us the research scope, the data set I used, the data processing, the data pre-processing steps, the detail about the formal concept analysis, the detail about the lattice theory approach, and the detail about the lattice augmented approach as well. So I'll start with the research scope. Now, I will give more detail about the three data sets I used here, but I'll start first. We have our OPAM data sets. Now we perform different processing steps on the data set. And the first objective was to compare different supervised machine learning approaches, such as a linear regression, gradient boosting models, random forest, decision tree, and extreme gradient boosting to find out which one will be able to predict the fruit level ripeness and oil content, as well as oil volume in different types of oil palm and in different positions. More on that. We evaluated the output with the mean square error, the mean absolute error, and the coefficient of determination, we call R squared. Now, for objective 2, we started to create the climate-aware provincial yield modeling. Now, instead of using all the models, the results from the first objective made us select the models we used in the second objective. And that was linear regression, random forest, gradient boosting models, and extreme gradient boosting model. And again, for the performance metrics, we measured that with root mean square error, mean absolute error, R squared. Now, the third one is the lattice augmented interpretability plus FCA, which is the approach we are proposing. And now this is where we'll talk about the FCA-based conceptual views, where we'll take a look at the leaf view, the tree view, the predicate view, the interordinal views as well. And we also look at the interpretability output, such as the leaf view size, the lattice depth, and the branching factor. Now, let's take a look at the data set we used first for objective 1. It's a primary data obtained from southern palm oil industry in Surat and the province of Thailand. Now, this data was gathered in real time using an IoT device shown in figure 6. Now, after that, the data were taken to the lab where an extraction was done using figure 7, the subtext extraction instrument. And a sample size of 30 seedlings was recorded and used. Data collection spanned 2 months for this objective, and it was from February 2023 to March 2023. And the data was collected continuously daily throughout this period. Now, only 2 to 3 samples were tested, and to ensure that there were no missing value, the accuracy and the completeness were top-notch. All efforts were made to avoid the missing value because originally we had a limited sample collection. We don't want to have a missing value for this. Now, here is what we did. We looked at oil palm we looked at 2 stages of oil palm, the ripe oil palm and the raw oil palm. Okay, in those 2 stages, we looked at different positions, 3 different positions. We have the top position, the middle position, and the bottom position. And what we're doing in this part of the research is to measure percentage of moisture content that can give us an oil content to see what we have. Table 1 has details regarding the data sets where we have the moisture ripe representing the moisture percentage in the ripe fruits, that is the ripe oil palm fruit, Oil ripe simply means oil percentage in the ripe fruit. Moisture raw is the moisture percentage in the raw fruit. Oil raw is the oil percentage in the raw fruit. With the stages and with the positions we are measuring and with the variables we had, we were able to calculate 12 measured values per seedling. And since we have 30 seedlings for this objective, we had around 360 data points. That is half of the data set. Now, again, we went ahead and looked at another set of oil palm stages. That is the semi-ripe, which you can call the underripe, and the ripe oil palm. This time around, what we're trying to do is to predict actual oil volume using sensor readings. Now, table 2 provides the details regarding the dataset structure, where now you have the top, middle, bottom. These are the sensor reading from the top position of the oil palm fruit, from the middle position, and from the bottom position. And we took the average of these positions, and the oil volume is the measured oil extracted. Overall, in this part of the research, like I said, we had a 30 seedlings count. We're able to obtain 300 total data points. So objective 1, we had 660 data points to use. More on the result of this objective later on. Now for objectives 2 and 3, we had the provincial oil palm production data. This was obtained from Jutapon and Tekwich in 2024. It comprises of 77 provinces, and it was from 2008 to 2020. It has 985 complete observations with no missing value. The structure of the data, again, is provided in table 3, where you have the year, which is the year of record of the area harvested, the quality of the production, and the yield, which is the target variable in this case. Moving on, we also obtained regional climate data from the Office of Agricultural Economics. But this was a macro region here, whereby we only had 4 regions. That is the northern region, northeastern region, central region, and the southern region. The data is from 2011 to 2020, and the structure is presented in table 4, where the region now is the macro region I defined earlier. The rainfall is the total annual rainfall in that region, and the raining days is the number of raining days in that particular region as well. Now, so those are the data we used in my research. Now, let's go to the pre-processing part. For data, for the objective 1, where we're measuring the top, bottom, and the middle position, there weren't really any processing steps to be taken there. But for objectives 2 and 3, where we have the oil production data and the rainfall data, we decided to embark on a province region mapping. Now, since the rainfall data was in region and we had 77 provinces, right? We needed to arrange these 77 provinces into one of the regions, right? And we did that using the official National Economic and Social Development Council classification in Thailand. Now, the northern region will contain northern provinces, right? The northeastern region contains eastern provinces. The central region contains the central as the eastern provinces, while the southern region contains the southern provinces. I didn't classify it like this. This classification was done for the National Economic and Social Development Council. I just used classification in my research. And the key property here is that every province should appear exactly once in one region. No province should belong to more than one region, and no province should be left unclassified. After that, we try to assign climate to provinces. Now, rainfall is only known at the regional level, right? So the assumption we made is that all provinces within the same region experience the same rainfall and the number of raining days for a given year. I mean, realistically, this is not true, but like this is the best assumption we can make since we didn't have a very fine scale climate data. What does this mean? So for instance, in year 2015, in southern region, maybe the rainfall is 2,400 millimeters and the raining days is 180 days. This means that in all southern region province, either Songkla, either Sorata, or even Patani here, every of these provinces get the same. And this is one of the limitations of the study as well. Every provinces get the same rainfall amount and the same raining days. Now, so the data set merging and how we handle the missing value. Now, the key here is to look at the year and the region and to perform a left join. The problem we had is production data. Oil production data was from 2008 to 2020. Rainfall data was from 2011 to 2020. I mean, it's not matching up, right? So from 2008 to 2010, there was no rainfall information. It's a structural problem. What I did here is to keep only 2011 to 2020, and I removed the rows with missing rainfall or raining days. In all, the final data set is 63 provincial observations with the details provided in table 6. Now, after that, let's move to the methodologies we used in this study. I'll start with the formal concept analysis. So the FCA, it's literally like a new approach being used now, is a framework that is based on lattice theory that assists in information organization and the discovery of patterns and structures within objects and attributes. Now, FCA is really efficient because it adopts a human-centered approach, and it allows you to kind of explore different structures and reveal like relationships that have been hidden. What they do best is to transform a binary table data, which we call a formal context, into a mathematical structure or the concept lattice. And a formal concept lattice is defined as follows. If you have a pair A, comma B, A is a subset of G, is referred to as the extent, and B, subset of M, is referred to as the intent. Then the concept will satisfy the relationship below. Now, we're talking about explainability. We're talking about machine learning. How do we even use machine learning and how do we explain it? I had said before that machine learning are the models are black boxes. So most times what different authors do is to use this type of techniques, sharp, line, and decision rule. These methods have their limitations. So for example, sharp only has a local explanation. It has no structural awareness. The same thing for line. The decision rule, is a bit better than Lime and Sharp, but again, it has a limited hierarchical representation. And that is why FCA, through lattice theory, is the latest method or approach that can really assist in explaining the different patterns in a data set. Now, we found a study, Hanika et al. In 2024, it's a very recent study. He provided a framework using FCA on random forest. And he provided 4 different types of view. We have the leaf view, the tree predicate view, and the interordinate predicate view. What the leaf view does in the random forest case is that it shows where each data point ends up across the forest. Okay. For the tree, it uses the whole tree, but it shows how complete trees contribute to the decisions. Now, the tree predicates using a decision rule, and it shows where rules influences predictions and where sometimes the tree disagrees, while the last one shows the main decision and the logic without rule duplication. It's a very recent method, and we try to understand what they did, and we try to extend the approach to boosting method. Like I said, handicap was it for random forest. We extended it to boosting method. And what we did is to incorporate a residual-based scaling for gradient boosting models using a residual magnitude as a proxy for tree importance. And we also used gradient-based weights for extreme gradient boosting. And what it does is it captures both the first and second order optimization and regularization penalties. And the last one is we provided an algorithm-aware transformation to formal context extent to generate meaningful structural concept views. When we compare, so apologies, here is the like the workflow we proposed when we extended the idea Hanika proposed for random forest to boosting method. And when we compare the results with Hanika et al., you'll notice that the XG boost we proposed had a great accuracy, better accuracy than random forest. However, in the error part, random forest still produces a little error. So in fact, this method is efficient, but we can really say it's accurate. But in terms of random forest, it's the error is still not as bad as random forest. So, but it's a good approach. Now, with that in mind, we're able to do this now. What we then needed to do is to, like I said before, classification papers are a lot in study of oil palm. We needed to transfer it back to regression-based boosting models. And what we did is we go back to the data we have. We have the oil palm yield data. This is continuous. Classification framework will not be suitable. Hanika's proposal was it's a discrete output. It uses a class decision. For us, we'll be using a leaf decision with yield production pattern. In our case, the concepts are not classes, but they are yield pattern in the agroclimatic space. Now, we define our resident weighted leaf as follows, as LGBM and LXGB. GBM in this case represents the gradient boosting model. XGB represents the extreme gradient boosting model. And what this simply means is we are looking at the complexity weighted by how much error each rule will explain. And we also looked at the pure count of how many different rules will exist. I in the definition represents the index for data points, which means, for instance, which provincial observation are we trying to look into? And M is the index for trees in the ensemble, meaning which boosting nitration are we talking about? And with this, we're able to define our own leaf view size, our own tree view size, our predicate view size, and our insubordinate predicate view size. With the meaning as follows. In our case, the leaf view means the number of distinct yield patterns. The tree means how complex is the ensemble structurally. The predicate means how many conditions or rules are used. And the interdependent predicate view means how hard is it to compare concepts across trees. Now, the performance checks we employed were the root mean square error, the R square, which is the coefficient of determination, the generalization error, the lattice depth. And you will notice that all these errors have a different unit to make sure that everything can be comparable with normalized all the outputs to 0 and 1. Yes, now to the results and discussions for objective 1. In the top position, we notice that the graded boosting model and random forest performs better for predicting ripe fruits, oil palm fruit for oil context. In the middle position, we notice that the decision tree and random forest performs better. In the down position, decision tree and graded boosting models perform better. That is for ripe fruit. For raw fruit, random forest performed better in top position. In the middle position, gradient boosting models, decision tree, random forest, and XG boost all performed good. In the down position, decision tree, gradient boosting models, and XG boost performed well. Now, for the semi-ripe and unripe fruits in oil volume and content, decision tree and extreme gradient boosting performed well for semi-ripe, and for unripe, again, decision tree, extreme gradient boosting, random forest, and gradient boosting models performed very well as well. So this is the result obtained from the first objective we're proposing. Now, the second objective, which is to look at the second and third objective, which is to look at how our model will perform when we move it from a classification approach to a regression approach. We'll start with the baseline performance yet without anything. Now, we assessed that under a 5-fold cross-validation. We'll notice that XG boost performed better. How do we know it performed better? Because it has the accuracy is top notch, which is the R squared. It has a low RMSE, it has a low MAA, and it has a high R square, like I said before. So in this case, when we look at the baseline performances, XG boost performed better. Now, when we look at the lattice augmented evaluation, where we take the number of trees, which we call N estimators, to be between 50 and 100, and the maximum depth to be between 2 and 5. Again, when you look at the RMSE, gradient boosting had a very little RMSE, but XG boost still had a better one in this case, which is 1,307.9.67. When you look at the leaf view, the method did not perform well for gradient boosting because it would take million trees to be able to achieve an estimation of 50 with a depth of 2, which is not really good. When you compare that with XG boost, which it just needs a 198 leaf view, and for 50 to 2 depth, and 951 for 50 to 5 depth. Again, XG boost performs better, even when we move the method from a classification method to a regression approach. Now, would like to compare both. Okay, what is the best trade-off using a Pareto Frontal analysis? Now, we increase the estimators to 300, but we maintain the same maximum depth. Again, we didn't even find any solution from gradient boosting model. the only solution, the output returned was XGBoost. An XGBoost with a maximum depth of 2 and an estimation of 300 performs best in this case. Now, what can we say about the methods we have? Now, in the first objective, the strength of the linear regression method is that it's simple and interpretable, but it has a very poor accuracy. Random forest has a good accuracy, but it's really hard to explain structurally. Graded boosting has a strong learner, but conceptually it is explosive, and we're unable to really combine that with FCA. But from the results we obtain, XGBoost has the best accuracy, and even though it has a slightly more complex training, it's much better than the gradient boosting approach. Now, when we compare the method based on criteria, how pure the prediction is, how accurate it is, when we look at the FCA and the lattice compatibility, and when we even looked into the Pareto optimality, XGBoost performed very well. Why you have the XGBoost only in the Pareto optimality is because that's the only, it didn't report any other method, it only produces XGBoost. But in the other criterion, other methods were produced, just that XGBoost performed better than them. Now, we can't just have a model and it has no implication. What is the implication for model selection? So for instance, right, we have different stakeholders, and these stakeholders can use our result in different ways. So for instance, these are the farmers. Farmers will probably prefer simple models, right? Because it's easier to explain to them, though it is slightly less accurate, but it's not even transparent. It is just very good for advice, training, and quick decisions. So for instance, we can use linear regression to train farmers because it's simple, but though the results are not really good. For policymakers need a balance between accuracy and clarity. Now, the results must be accurate enough for planning. So we would have to look at a better approach. So for instance, for them, we can approach them with the gradient boosting model. This is what is happening. And if you provide these policies, Thailand will be better off in oil palm. Now, the government agencies want the best models, okay? Models that can handle different complexity. So in this study, the only one that can handle that is XGBoost. So what are the conclusions, limitations, and future works? The first thing is that from my research, I realized that machine learning models are really effective in modeling oil palm productivity, both at the fruit level and at the provincial level. At the fruit level, like I showed you before, different model performs best depending on the position and the ripeness. This means that policymakers should really be interested in looking at the positions and maturity details of oil palm. The inclusion of FCA with Ensemble now can provide more clarity to the government on the decisions they need to make to kind of just improve the oil palm production in Thailand. Now, one key thing about my study is that it combines the predictive power and the explainability part to yield forecasting. And with this, the government can actually plan. They can be climate aware and have provided an evidence-based policy detail for Thai policymakers to really implement this in Thailand. Now, here are some of the limitations. One of the limitations is the data set, right? Because it's only limited to rainfall and rainy days. And these might not actually capture the complexity of the problem with oil palm in Thailand. I mean, variables such as the temperature extremes, the solar radiation, and even the soil moisture were not really captured. Okay. Now, the provincial analysis relied on annual data. So we didn't really consider seasonal patterns in the data. Also, the framework I used was primarily tested on ensemble models, particularly XGBoost and GBM, and not on deep learning or hybrid mechanistic models. So future research could also look into that. I would say here that this study remains observational and predictive. So, I mean, the government should kind of just look at it that, okay, this is the first study providing these types of detail to us. So here are the future works you can consider from this study. Like I said, we can enrich the data sets. We can add temperature extreme. We can add solar radiation. What this will do is to allow us capture the full environmental drivers of oil palm productivity. Next, we can apply the framework to other crops. This is only oil palm. We can test for soya. We can even test for rice, which is a major staple in Thailand as well. And lastly, we can even extend the lattice augmented interpretability to other modeling approaches, such as random forest. In my study, I did for only gradient boosting models and extreme gradient boosting models. We can do that to deep learning models and hybrid mechanistic models. So here are the articles we're able to publish from the research. The first objective was published in Acta Agrobotanica, while the second objective, half of the second objective was published in Intelligent Systems with applications. So to the acknowledgements, I would like to thank the committee members, most especially Achan Lao, Achan Salang, and Achan Aperat. I sent a lot of emails. Thank you so much for making time out to listen to my supervisors, Achan Pakwan and Achan Jarapon. Thank you for always being there. And to the program assistants, I literally don't know how much I disturbed Maprang. Sorry, Kun Maprang for everything I needed. So she was very helpful. Here are the references for the study. Thank you for listening.